We often try to distinguish between what is alive and what is a machine, and note that machines cannot reproduce or fix themselves, but that may soon change. In the verdant suburbs of the future, nestled between lush green hills and a sparkling river, stood a quaint house that was known among locals as the Living House. It was the home of Susan, a world-renowned robotics expert whose home always had the latest and greatest advances in robots on display, many years before they came out on the regular market, or prototypes that never were for sale, and were unique to her abode or a handful of other colleagues. Miss Calvin's home had robotic integrations on everything, even the kitchen sink. When a bad storm came by and knocked free many roof tiles in the neighborhood, Susan's house seemed untouched, as drones had come out after the storm to readjust and replace those moved or broken. While her neighbors used robots to mow their lawns and favor low-maintenance gardens, Susan's garden is as elaborate as you'd see in any home and garden magazine, carefully tended by small robots who even harvest her vegetable and herb garden for her. It's not the immaculate lawn or hedges, or the sparkling clean house that's the true wonder though. Instead is that the Calvin household hasn't had to call a repairman in years. The house knows every problem as it pops up, and what it can't fix itself, it can send you a detailed DIY video for, and with your permission even have any specialized tools rented and shipped to your location. Even this pales in comparison to newer features, the self-repairing concrete that can fix any crack in the driveway or foundation, paired with diagnostic tools that help predict and avoid such cracking. The same features in the very bones of the house, a self-repairing frame that no termite, mold, or wear and tear will bring down. Susan's home pressure washes itself, cleans its own windows, seals any cracks in them, and repolishes the glass to perfect transparency. The carpet grows on a specialized nutrient like fur or hair and gets seamlessly mowed and cleaned. Walls get cleaned and even repainted, and cracks or holes in the organic drywall get sealed. Every pipe and duct and vent sparkling clean and leak-free. Miss Calvin's home is always in perfect condition, and maintaining it this way costs only a fraction of what typical maintenance does. This is Susan's home, and it's coming to a neighborhood near you soon. The notion of self-repairing machines has long captivated and terrified our imaginations, with roots extending deep into the realms of science fiction, where it represents the promise of incredibly useful machines coupled to the dangers of ones that would seem to mimic life itself. The technology is leaving the realms of pure science fiction and transitioning to tangible reality, driven by advances in robotics, material science, and artificial intelligence. And today we'll be looking at each of these pathways to self-repairing and even self-replicating machines. Why is this seen as useful though? Why is self-repair such an advantage? Fundamentally, a machine has a handful of big costs. Besides initial costs, we have operating costs, which tend to rise as a machine breaks down, and maintenance costs, as well as training costs when you buy a new and upgraded model, or even just a different one. And you inevitably need to buy a new one because the cost of replacing every part on the spot over and over again as they individually break is always going to be higher than manufacturing a new one in a dedicated factory somewhere. A lot of components tend to break around the same time, just from being made of the same basic materials or built around the same philosophy. And we have this popping up a lot this year in my home. We bought a house a few years back that was manufactured about 20 years prior, and I delayed on writing the script because the HVAC guys were doing the furnace and AC, which are pretty close to my office. One of the guys in was the same one who had diagnosed the water heater a few months back and said get ready to replace that this year or next. And a lot of other issues like plumbing and worn cabinets and fixtures have started to pop up. It's just the general life cycle. and we often don't bother with more expensive and durable components on made devices because paying twice as much for an individual piece that's going to last 3 times longer is only a good deal if every other part in that device can be likewise enhanced. Why put a 30-year piece of hardware in a cabinet that will wear down in 15 or 20? But this game changes a lot if those folks doing those repairs don't have to be humans coming in on service calls, if the device can instead fully fix itself, or even just those bits of wear and tear that would be routine and too expensive to fix. What if you only fix something by fixing the design flaw one time, and all the objects with it can now apply that themselves, akin to a software patch on a computer? As a side note, self-repairing machines can include the idea of one's able to self-upgrade or patch, as modern computers do with their software, at least in terms of opening and applying them automatically or on command. Software is part of self-repair, especially for anything sophisticated, though also one of those more dangerous self-repairing items to allow. So if things are self-repairing, even just in large part, that really cuts down your operating costs after buying it, as you keep it longer and it needs less repairs and associated costs like training or refitting devices nearby or that work with it. Also, the initial purchase cost is lower if a lot of the machines involved in making it are lower in operating costs too. We usually say that after buying a house, you need to expect to put 1 to 2% of its value back into it for maintenance every year, another hidden cost of ownership along with property taxes and insurance. How much do houses cost if you only have to build them once, and they almost entirely self-repair after that, even if it just drops to 0.1% to 0.2% instead of 1% or 2%? How much cheaper is that home if all the tools used making it only had to be replaced half as often, and the factories making the lumber and other supplies were doing it for half the price because their equipment costs were lower and they could often afford higher quality tools because they wouldn't break often and similarly were produced cheaper at their own factories? Self-repairing machines are a lot like abundant renewable energy. They result in a lot less waste and make everything cheaper along the way. However, let's add an early caveat. In many ways, the ability to quickly and cheaply manufacture new devices as replacements does limit the gain made in self-repair, but it depends on the machine. I don't really need a self-repairing pencil, for instance, but it would be nice if it could refill its own pencil lead and eraser, or even if smart systems just knew how often I went through them and knew to order me some more. This is probably just as easily accomplished that way as a practical goal though, or by a drone or smart house that can pop by, see the supply of either, and replace it or refill it. We shouldn't focus on advantage of self-repair to the point of ignoring that the machine has a role it is doing, and what we actually care about is that the mission is getting done. The machine is not alive and, except perhaps for advanced AI, is not a thinking, feeling critter we should feel sorrow about replacing. One thing that comes up a lot with self-repairing, self-replicating, or intelligent machines is the habit of viewing them strictly through a biological lens. In nature, other critters rarely have potent symbiotic relationships, and even when they do, it's not going to result in a complex multi-species interaction to achieve a goal like refilling Isaac's pencil lead so he can make notes for episodes. But we can have ecosystems of machines designed to work together on tasks. So while contemplating self-repairing machines today, we also want to keep in mind options like machines tasked with responding to maintenance calls, or using some other machine to manufacture a given type of machine rather than self-replication. And that's an important place to begin, because to repair yourself, you need to be aware of the fault. The development of machines that can detect their malfunctions and initiate corrective actions without human intervention, including summoning help from another machine, could revolutionize industries by reducing downtime, lowering maintenance costs, and extending the operational lifespan of machinery. We should note though that even just a machine able to simply and accurately tell a human the problem and attach the detailed DIY video on how to fix it is an excellent and incredibly useful first step toward self-repair. And in some cases, where we are concerned of machine revolts and rebellions, it's not a bad idea to have humans as a necessary step in self-repair replication, and decision-making, and often a machine dedicated to just creating more of one specific machine on a request will be better at it than one designed to do its own job and self-replicate, or its own job and self-repair. Very often, it will depend on the circumstances. This episode will not just explore the technology behind self-repairing machines, but this interlocking ecosystem approach too. Our main focus, though, is the current state of the technologies, paths for progress, challenges, ethical considerations, and the general future prospect of these kind of technologies. Let's start by outlining the key technological foundations, and they are, in short, sensing and diagnostics, advanced materials, robotics, and artificial intelligence. On the back end of that, we'll talk more about emulating biology and also innovating beyond biological limitations. Sensing and diagnostics. As we mentioned, self-repairing machines require sophisticated sensors to continuously monitor their condition and performance. Even simply having the ability to detect problems and let us know of them to repair ourselves is a major advantage in machines. They are absolutely essential to more advanced self-repair technologies too. You cannot fix a problem if you don't know it exists and how to fix it, and that means having many of the appropriate kinds of sensors. These sensors might collect data related to wear, temperature, vibration, and other critical parameters. It is amazing what sort of details we can get, forensics and CSI style, from seemingly unrelated and minimal sources, and that's all the more potent when the sensors are purpose-built to find the sorts of errors that the device tends to exhibit and monitor it constantly for early warning signs. Prevention is the best maintenance, and early detection lets you tweak a minor problem before it avalanches. This can be non-obvious stuff too. A simple pressure sensor in a tire can be used to detect leaks or tires needing replaced, but it can also help you extrapolate a problem with an engine or brakes if you see a drop in mileage or some other issue that might be easy to spot when you know the condition of the tires very accurately. So too, a temperature sensor tends to be a very good early warning system for many faults, as often anything misaligned or broken is going to generate heat from friction or electrical faults. Acoustic or vibration sensors can detect misaligned parts or cracks in a material even before they might be visible to our eyes, especially when a component may be hidden from sight. Simple measurements of electrical resistance in a material can warn you that it is beginning to corrode or degrade, and pressure sensors can spot leaks or clogs. Nothing very complex in function, cost, or computation is necessarily required. In many cases, very simple, tiny, and cheap pieces will work. More sophisticated ones probably are better, but may not be worth putting on a given machine. This is one of our examples of where self-repairing doesn't have to be entirely located in that device. Your car may have many sensors in it, but so too your garage might, which could be integrated into your diagnostics. Or the local gas station or charging station might have such diagnostics available for a small charge like vacuums or air pumps often are now, or even complimentary to draw customers, as they might be able to afford very elaborate sensors compared to what an individual car or personal household garage might. So too, a cloud-based approach might be superior to simply having onboard diagnostics. Nature is often an excellent source of inspiration for machinery, but we must not limit ourselves to it for inspiration either. Your car is going to be integrated into the internet anyway, same for your house or lawnmower or almost any new appliance or other technology. So while onboard diagnostics are still vital, connectivity to other more sophisticated systems off-site helps you while also sharing new problems and the frequency of common problems to others to help improve everybody's system. This is also ideal for AI, especially in order to help make it fast, low cost, and enhancing options for personal privacy, but we'll come back to artificial intelligence in a moment. Our next category is advanced materials, because not everything involving self-repair needs to include robots and computers. Self-repairing or self-healing materials are a rapidly evolving field in material science, with applications that span from engineering to biomedicine. These materials have the intrinsic ability to repair damage caused by wear and tear, which can significantly extend their lifetime and functionality. The development and integration of self-healing materials are particularly impactful in industries where material failure is a critical safety concern, such as in aerospace, civil infrastructure, electronics, and the automotive sector. As the most obvious example, imagine if you never had to repair a road, driveway, sidewalk, or bike trail again, as opposed to almost constantly needing to fix them and usually completely redo them every decade or so. Not only do we save more fuel from better maintained roads, but that cost savings can be used for other projects, like building more bike trails, or return to taxpayers or consumers. Self-healing materials fall into a handful of general types and categories. The first is autonomic self-healing materials. These materials do not require any external diagnosis or intervention to start the healing process. They are designed to respond automatically when damage occurs, akin to biological organisms on Earth. This category can further be divided into capsule-based systems and vascular systems. Capsule-based systems contain microcapsules filled with a healing agent and a catalyst. When the material breaks, the capsules break, releasing the agent that flows into the crack and polymerizes, often with the help of a catalyst to repair damage. At a larger scale, in our recent discussion of shell worlds and hollow earth megastructures, we point out that the variety that were full of compressed gas in their center, with the landscape above separated by some layer of firmament, might use larger balloons of high buoyancy gas to go wedge up into any large crack as it occurred and plug a leak till it could be better sealed, like a scab, and that's an example of a capsule. But we might make that more sophisticated by having the thin membrane of that balloon be full of that healing and sealant agent, so that as the balloon wedged in and stuck and started getting scraped and shredded, that membrane healing agent would leak out where it needed to be. Self-healing artificial planets are a little beyond our scope for today, but the concept also applies to spaceships, space stations, and larger rotating space habitats. Another way you might do that is by having lots of transport arteries through a hull for moving a healing agent around, much as you would a coolant, and much as we do with blood, which is also our default bandage material, again scabbing. Vascular systems like this are similar to the circulatory systems found in biological organisms, but not necessarily limited by the same constraints nature and evolution would tend to demand. For instance, you don't necessarily need to limit yourself to one heart or pump, or one sealing agent, and while multiple heart equivalents do exist in nature, they are harder to evolve. Vascular healing materials have a network of hollow tubes filled with healing agents. When damage occurs, the agent is released into the crack through the vascular channels to mend the material. This might be a simple scab-like repair, or a flow of liquid containing many smaller capsules, or something more sophisticated. Again though, we are not limited to biological analogies, and in addition to autonomous self-healing materials, we also have non-autonomic self-healing materials. These materials require some external trigger to start the healing process, such as heat, light, or manual intervention. Heat-based or thermally activated materials would be examples of polymers and composites that can heal cracks when wanted. The heat partially melts the material, allowing it to flow into the cracks and solidify upon cooling, thus healing the damage, and is conceptually akin to welding or soldering a crack. Photoactivated healing might be by materials incorporating light-sensitive compounds that, when exposed to specific wavelengths of light, can initiate chemical reactions that repair the material. You may have seen or experienced that at a dentist, where a blue light wand is used to cure a resin for fillings. We could also hypothesize magnetic or electric activated systems, or acoustic or vibrational ones. Also, some materials like memory metal we could think of as inherently self-repairing, in whole or part. With that in mind, there's also mechanisms of healing. Principally, this is going to be physical, chemical, or software, though we could throw in both biological and psychological healing for more advanced technologies. In physical healing, the material undergoes physical processes such as melting, diffusion, or mechanical forces that bring the fractured surfaces together. This type often results in reversible changes, meaning the material can undergo multiple healing cycles. Alternatively, chemical healing involves chemical reactions at the site of the damage. This can include polymerization reactions or cross-linking processes that restore the material's structural integrity. Chemical healing is generally stronger than physical healing, but may not be repeatable without the addition of new material or catalyst. Software healing approaches are obviously on the computerized side of things, and would merely be advances on the patches and updates we know all too well. As for applications of self-repairing technologies where self-healing materials are concerned, we already noted roads, and this would expand to include bridges and other civil engineering projects, as well as homes. This could incorporate bacteria or healing agents that activate in response to the presence of water and cracks, as is the case with one of the most promising approaches to self-healing concrete. The bacteria produces limestone, effectively sealing cracks and increasing the material's lifespan. Aerospace and automotive applications is another big one. Cracks and fractures on an aircraft's wings or any vehicle surface can be deadly and are expensive to check for and repair, especially on many critical components under the surface that are hard to get at to inspect or repair. For electronics, self-healing materials can be used in circuits and batteries to repair breaks or degradation that occur during usage, thus extending the life of the devices. Despite their promising benefits, self-healing materials face several challenges. The efficiency of healing, the speed of recovery, the repeatability of the healing process, and the mechanical strength after healing are critical parameters that need optimization. We may find replacement is cheaper in many cases, and a thing to keep in mind is that even as these technologies make repairing existing devices cheaper, these very same technologies and some related applications can make manufacturing new ones cheaper, as well as making the recycling of old ones cheaper and easier. Additionally, the economic viability of incorporating self-healing technologies into mass-produced products remains a significant hurdle. Odds are good there will be many devices it is cheaper and better for, and others where automated production and automated recycling of garbage make outright replacement of a faulty device better. Again, I don't need a self-healing pencil. Our next category is robotics, and while this blends over into AI, I do see it as fairly distinct in most cases. In the smallest case, and analogous to bigger organisms with their own immune systems and ecologies of microorganisms inside them, we could have nanobots doing a lot of inspection and repair work to virtually any object, including humans, on the orders of some larger sensing, diagnosing, and controlling system. Robots can be incorporated into other niches we discussed too, such as the modern drone with an infrared camera scanning homes for signs of leaks and cracks, or the nanobots in a capsule or vascular system that are the healing agent for a material, or the larger micro-robot that is closer to cell-sized and inspects your arteries for blockages, or removes them or finds cancerous cells and reports them or zaps them. This is another example where a more complex ecosystem approach can be handy, having many specialized robots with different roles, sizes, and capabilities, and less biologically inspired ecosystems, where reproduction is handled by an entirely separate quasi-organism, rather than self-replication, a microfactory producing a given type of nanobot. Bots that do not self-repair, just report that all is well while working, and thus leave an easy trail to follow to recover them, see where they left off at so another can be assigned, and tow them back for repair or recycling. This is a good approach to avoiding gray goo scenarios, where some machines able to replicate themselves and act as all-purpose constructors and assemblers go haywire and turn your whole planet, including the people living on it, into more of these little robots. But it's also recognizing that self-repair is an awesome approach, but not necessarily a one-size-fits-all solution for everything. We've mentioned how these same sorts of technologies will often make manufacturing replacements and recycling damaged ones cheaper too, so that it might rival or surpass self-repair for cost and practicality in some applications, but is also related to concerns about self-replication and other general ethical problems of abuse. Which is a good place to segue into our last category of artificial intelligence, as it can be wielded to both help and harm us, particularly in the category of privacy. An AI can sift through mountains of data and reports of 1 million machines in 1 million households, and if used wrongly and without the right safeguards, violates your privacy in almost every conceivable way, what with all those sensors and detectors everywhere, which can be used in novel fashion to record stuff beyond that machine, like you and everything you're doing. Used correctly, it can ensure we get all the data we need to make better devices that better serve us and last longer while removing all personal data from the equation. It can even do this after the fact, since unlike a human, you can have it get all those personal details to make very good judgments, then delete those details and be left with only the general judgments. We'll be talking more about privacy in our September 2024 episode, Is Privacy Going Extinct? So we'll leave that there for now. Needless to say, AI is handy for detecting and diagnosing problems, and activating repair mechanisms, but it is also great for monitoring if the repair actually worked, and running through simple troubleshooting steps without asking you every time, up to and including rebooting itself, which is so often the easiest fix. But beyond that allows self-optimization, as well as communication with other sibling systems to improve performance and remove problems. This includes both identical ones in other people's homes or devices in your own that work in conjunction with it. Your AI might be able to spot that your air filters in your home are clogging too quickly and realize it's because your robot vacuum always parks right next to it, because you put them in the same closet, and often dumps dust into the filter if that's on while it's offloading the dirt it got in the waste bin next to its charger. Then it alerts every vacuum and every air filter that they should be mindful of that problem themselves, and you get a note that one of them needs to move, or the manufacturer sends down a suggestion for putting up some sort of dust shield maybe. Nothing complex or revolutionary, that might come sometimes too, but often all real advances and progresses aren't one big thing, but 10,000 mundane things. And when it's made of many small steps forward, it's often easier to accomplish. Another way technologies like this can resemble nature. Their evolution often works easiest when made of many small steps, each of which has some value. It also gives us time to adjust and not be swamped under a massive and sudden technological disruption, but instead many small and steady minor improvements, with some bigger and more impactful ones popping up occasionally too. While the dream of fully autonomous self-repairing machines may still be somewhat in the realm of science fiction, as we saw, the foundations are clearly being laid today. The convergence of multiple advanced technologies points toward a future where machines are not only disposable tools, but resilient partners capable of self-preservation. This evolution will doubtless reshape our relationship with the machines on which we increasingly rely. Ultimately, the concept of machines that can autonomously maintain and repair themselves represents a significant step forward in the evolution of technology. As these machines become more sophisticated and reliable, they promise to transform our industrial landscape, making it more efficient, sustainable, and adaptable. The journey toward fully autonomous, self-repairing systems is still in its early stages, but the potential impacts and benefits suggest it is a path worth pursuing, and be a pathway to our other dreams beyond Earth into space, where self-repairing and even self-creating machinery may be vital to forging our future among the stars. We talked a lot today about how machinery can be improved by emulating nature, and we could do an entire episode just cataloging all the times we learned some new technique from something we observed in our environment. It is impossible to calculate all the missed opportunities we might have from lost ecosystems or extinct species. That's where organizations like Planet Wild help, and you can join their community to do your part in protecting biodiversity around the globe. Each month, Planet Wild teams up with conservation pioneers around the world and supports their work at the front lines, identifying what needs to be done to protect endangered ecosystems. Since they began in spring of 2023, they've completed 17 rewilding missions so far. Every month they travel to and document a new project. Their YouTube channel does top-notch, long-form science education content focused on those innovative conservation and rewilding projects. You can watch one of their videos in my description box. In that mission, they rewild barren area underneath power lines to restore biodiversity. If you'd like to join their community and help crowdfund for nature, you can give whatever amount, big or small, that feels right to you, and basic membership is just the cost of a couple cups of coffee a month. But the first 150 folks who join by going will get their first month membership paid for by me personally. You can cancel anytime, no questions asked. If you want to dig deeper, they offer a complimentary app which gives you reports and blog articles on each mission and lets you connect with like-minded people in the Planet Wild community. Check out the link in the description, click this QR code or use the code Isaac27 later. Together, we can make a difference. So that's it for today, but join us this weekend as we wrap up July with a journey to the moon to contemplate mobile mining platforms and life as a lunar mineral prospector or nomadic miner on the moon. Then we'll start August off by joining Colonial Governor Maxwell Augustine and the Olympic Fleet migrating to the planet of New Actium as we see what it would be like to be the governor of a generation ship and a fledgling colony. After that, we'll return to the topic of the Fermi Paradox on August 8th to consider how migration to the galactic core or rim or other universes might explain the Great Silence. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, along with hours of bonus content like Planetary Archives and Stasis Vaults at go.nebula.tv/isaacarthur. As always, thanks for watching and have a great week.